Hello and welcome to MT3. We are on our second lecture, but this is part B of it. Now we're looking at partial differential equations, the method of separation of variables, and just to remind you, we are following Arfken, Weber, and Harris chapter 9, and Riley, Hobson, and Benz chapter 21. Now we've already seen how this technique can be applied to the wave equation, shown here, and to the diffusion equation shown over here, but and I've shown you that. But now we'd like to look at a way of getting a full solution, and this is going to be our first example where we actually find the entire solution through a superposition of solutions. Now one of the things, so what is the superposition of solutions? It means we are going to solve for psi of mn and write down the full solution to the partial differential equation, including boundary conditions and the initial value condition, as a linear combination of these things with coefficients a, m, n. Now you'll understand what the m and n actually signifies soon, but just to remind you, when we wrote down our solution to, let's see which one it was, to the wave equation, we wrote it down as, we indexed it with n. So psi n was related to, was defined to be a n times this exponential involving the constant n, where n turned out to be an integer here, positive or negative or 0. So that becomes our solution for a given n. Now what we're going to see is that the general solution to a complex problem will normally involve an infinite number of these terms in a linear combination. But each of these solutions effectively becomes a basis function for our space. All right. This will be clear once we actually solve things. So let's just get on to solving stuff. Okay. Now here's the problem at hand. We are going to solve Laplace's equation. So this is Laplace's equation. The Laplacian of psi is 0. We are solving it within this parallelepiped. So we have a rectangular box with faces at 0, x is equal to 0, a face at x is equal to c, y is 0, y is c. So the box should have had a square face at the bottom. Sorry, it doesn't. And then we have faces at z is equal to 0 and z is equal to L. Now the boundary conditions are as follows. We're going to apply a potential. So psi is the potential here. In electromagnetic theory, electrostatics in this case, and we have a potential of V, so this is a constant, on the upper face, so the face where Z is equal to L, and it's 0 elsewhere. So if you want to imagine a physical problem, you're applying a potential to a plate over here, but you're grounding all the other faces, so they have 0 potential. And what you want to know is what's the potential at any point in this box. Okay, that's what the solution is going to represent. So let's put down our boundary conditions then. Psi is 0 on the faces except the face where z is equal to L. Here psi of x, y, L is a constant which is equal to V, our potential. So this is the Laplace's equation in x, y, and z coordinates. And now we're going to use the ansatz that psi is capital X, which is a function of little x, capital Y, a function of little y, capital Z, a function of little z. Now I'd like you to show, and you can, that if you put this in here and then you divide by x, y, z, capital X, capital Y, capital Z, you will end up with the following equation. Now the solutions, I'm following the solution which is with some minor modifications, which is in Arfken's book, so you will find some of the missing steps there. So this is something we need to show. All right. And now let's move the x terms, keep only the x terms on the left hand side, and move the y and z to the right hand side. So what we get is the equation here. So now we've got on the left hand side, sorry, my left and right seem to be equivalent. On the left hand side we've got something which is a function of little x only. Capital X, remember, is a function of little x, And on the right hand side we've got functions which are functions of little y and little z only. And this equality has to hold for any little x, any point in space in that parallelepiped, and any y and z in that parallelepiped. So the only way this can happen is if these are both equal to some constant k. I don't know yet what k needs to be, I just call it k. Alright, so therefore we end up getting x double prime minus k times x is 0, or x is equal to e to the plus and minus root k times x. Now, before going any further, let's try and use the solution to get an idea of what k might be. So, to understand what k needs to be, let's see if we can apply the boundary conditions. Now, the boundary conditions are that when the boundary conditions as applicable to the x coordinate only, those are the only ones which apply to capital X. So psi of 0 with any y and z is 0, and psi of c with any y and z is 0. This is just a statement that psi is 0 on the face x is equal to 0 and x is equal to c, which means capital X of 0 is 0 and capital X of c is 0. Okay, I hope you see this, because the only the boundary conditions applied to the x coordinate will therefore will apply to the function capital X. Therefore, these are the boundary conditions for the function capital X. Now, if k is greater than 0, then capital X is simply a linear combination of these two exponentials, e to the minus k root k x plus b e to the plus root kx. Now the boundary conditions imply that a plus b is 0, so that's when x is 0, we'll get a plus b is 0. And then the other boundary condition at x is equal to c implies that a times e to the minus square root of kc plus b e to the square root of kc is 0. Now from the first one a is minus b, so we then get from the second one b times these two the difference of these two exponentials is 0. But you know, when c is greater than 0, this is impossible. You can't satisfy this unless k is 0 itself. But we have required k to be greater than 0. So this is not possible. Alright, so we can't have k greater than 0 because we can't satisfy the boundary conditions along x. So can k be equal to 0? Well, if k is equal to 0, then the solution is that x is equal to ax plus b. Please show this. Now the boundary conditions again require that b is 0 and a times c is 0 or a is 0. Again, it's no good, because in both these cases what the boundary conditions have said is that if k is greater than 0 or k is equal to 0, then the function capital X is 0. That's the trivial solution to the equation, and we're not interested in that. We want a non-trivial solution, which means that we must have k is less than 0. And let's choose k is equal to minus lambda squared, where lambda squared is greater than 0. Alright, so we now know what k should be. So now we have x double prime. So when we equate x double prime over x is equal to minus lambda squared, we get this second order ODE for x. It's constant coefficients, so the solutions are of the form x is equal to a sine lambda x plus b cos lambda x. Now we can apply the boundary conditions. The boundary condition at x is equal to 0, capital X is 0, which means b is 0. At c, at x is equal to c, capital X of c is 0, which means a times sine of lambda c is 0, which means lambda times c is some integer times pi. Now here I have chosen this integer to be positive integers only, non-zero positive integers. So let's disentangle this. Why can we not have L is equal to 0? First question. Think about it. Why can't L be 0? Now, if you have thought about it, you should see that if L is 0, then we are going to get the sine of 0. Because if L is 0, lambda is 0, therefore we'll have sine of 0. Sine of 0 is 0. So we get, and b has been known to be 0 from the first boundary condition. So we get x is 0. Capital X is 0. That's a trivial solution. Now, what if, okay, so that's a trivial solution. This should be this, we're not interested in that. Why can't L be -1 or -2? Why is it positive only? Think about it. Pause the video for a while if you wish. Now, if you have thought about it, then what you should see is that, I hope you've concluded that if you have minus L, if you make lambda minus lambda, you simply get minus the sign of lambda x. It's nothing new. It's a linearly dependent function. It's just the minus of sign of lambda x. So, you don't get any new information by choosing the negative integers. This is why we choose L to be non-zero and the positive integers only. You could just as well choose L to be the negative integers only. Okay, we are biased to positive integers, so let's choose it to be that. So our solutions then are indexed with L, not N, with L, and they are of the form x of L, x subscript L of x is equal to a subscript L. This is an unknown constant at this stage, and the sign of L pi x over c. I'd like you to note something here. The argument of the sign, L is an integer, pi is a constant, a mathematical constant, x is a physical variable of dimensions, it's got dimensions of length, and c is a physical constant of dimensions length. So the total dimensions of the argument is, it doesn't have dimensions. And this is something you're going to see almost all the time. When you've got your arguments of functions like the sign correct, they will be dimensionless. And what this means, and the question is why are these arguments turning out to be dimensionless? And one way of looking at it is that the sign, you can expand it as x plus x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, etc. And if you've got a dimensionless, if the x has got dimensions, then what you're saying is that the first term has dimensions L, length, the second term has dimensions length cubed, the third term has dimensions length to the 5. This doesn't make any sense. But if the argument is dimensionless, then every term in that expansion is also dimensionless. And this is why we get such arguments in here. X divided by c, where c, both of them have dimensions L, so they cancel out. This is also a way of cross-checking. If you've got the wrong answer, if you find that your argument has got dimensions of a physical constant, physical quantity, then you probably missed something in there. So what about y and z? We've got the function of x. Well, to get a grip on that, we now look at our differential equation as we had it in the separable form. And now let's look at the second two terms only. So the minus y squared divided by y minus z squared divided by z is equal to minus lambda squared. So we'll put those down here. Now I will keep the terms in y on the left hand side and move the z terms to the right hand side. So we have y double prime divided by y is equal to lambda squared minus z double prime divided by z. Remember, these are functions of little y and little z respectively. And that's equal to, well, I'm jumping ahead. On the left hand side, we've got something that depends on little y only. And on the right hand side, we've got something that depends on little z only. The only way for these two to be equal at every y and z is that they must be equal to some constant. And once again, I anticipate this constant is going to be negative. It's the same argument we used for the x, for the constant for x double prime over x to be negative. Go over it if you've forgotten it already. But let's put this to be minus mu squared, where mu squared is greater than 0. All right. And following exactly the same procedure we used for x as a function of x, we get y as a function of little y is equal to b times the sine of m pi y over c, where mu is equal to m pi over c, and m takes over the positive integers. Now I should have said that we index this by m over there. All right, and then we are left with z. So to find out how to, an equation for z, we look at the we take this equation now, and we look at just this part of the equation. So I put that down here. This is the above equation for y and z. Now we look at just lambda squared minus z double prime over z is equal to minus mu squared. This gives us an equation for z double prime over z. That's equal to mu squared plus lambda squared. Well, we know what mu and lambda are. Mu is given by m pi over c. Lambda was given by l pi over c. Put that in there. That's going to be L squared plus M squared times pi squared over C squared. In other words, we don't need another constant for Z. We already know what it is, but it's tedious to write this down all the time, so I'm going to call it gamma squared. Alright, gamma squared is defined to be this. I don't need to solve for it anymore. So we have a differential equation, Z double prime is equal to gamma squared Z. Now, note something here. Gamma squared is a positive constant. It's greater than 0. It can't be equal to 0 because neither L nor M are allowed to be 0. And therefore, the solution for capital Z differs from the solutions for capital X and capital Y, because now we have the solutions for capital Z involve exponentials and not oscillatory. They're not oscillatory. So it's a times e to the gamma z plus b times e to the minus gamma z. Now we apply our boundary conditions. At little z equal to 0, we have capital Z is 0. So we have a plus b is 0, which means b is minus a. And at little z equal to L, capital Z is equal to v. It's not 0, it's v. And this is where, and this gives us this condition here. So we have a times e to the gamma L minus e times minus gamma, e to the minus gamma L is v, and this is just the hyperbolic sign. So it's a times twice the hyperbolic sign of gamma L is v. In other words, a is this constant v divided by twice hyperbolic sign of gamma L. So we now have an expression for capital Z as a function of little z. It's v times sine hyperbolic of gamma z divided by sine hyperbolic of gamma L. Now you're going to say, and I hope you say this, is wait a second, you've got z here depends on, it seems to depend on position, and therefore you've got something, the argument of the sine hyperbolic depends on position. Likewise here, that's not true because gamma itself has got a 1 over L in it through the C. So both of these arguments are dimensionless as they should be. Okay, now gamma is indexed by little l and little m. So z itself, this function z is indexed by little l and little m. So I'm going to write z of lm and gamma of lm to remind me of that indexing. Let's put it together. So now we have our solution to Laplace's equation is given by psi of Lm. Those are our two kind of quantum numbers which index our solutions, and this is a function of x, y, and z. And we have that's equal to capital X, which is indexed by little l, capital Y indexed by little m, and capital Z indexed by L and m. And you can put down the functions here. This is what they look like. Sine of L pi x divided by c, sine of m pi y divided by c, and then you have this constant v times the sine hyperbolics. Great. So we've got the a particular, so this is true for a particular choice of L and M. Of course, there are an infinite number of these L's and M's. So the general solution will be a linear combination. It's going to be a sum. L goes from 1 to infinity. It's double sum actually. M goes from 1 to infinity of A, L, M. A is an unknown constant. And times each of these psi L, M's. So we have a superposition of solutions. Now, before we go any further, let's just do a few checks. Does this solution satisfy all the boundary conditions? Okay, always nice to see. Is it 0, I think we'll need, yes, we need that. Is it 0 when x is 0? Well, if you put x is 0 here, you get sine of 0, which is 0. So yes, it is 0. Is it 0 when x is c? If you put x is equal to c here, you'll get sine of L pi, which is 0. So yes, it is. So that's the answer, yes. Is it 0 when y is 0? Sine of 0 is 0, yes. Is it 0 when y is c? You get sine of m pi, which is 0, yes. Now, is it 0 when z is 0? Well, sine hyperbolic of 0 is 0, so that is correct because of this relation. Is it 0, is it equal to v, sorry, not 0, when z is equal to L? Well, when z is equal to L, you're going to have these two terms cancelling out. And you're going to be left with a sum going over some constants a, L, m, which we don't know yet, of sine L pi x divided by c sine m pi y divided by c times this v. And, you know, we don't know what that sum is going to be. So not yet. It's not yet, this boundary condition is not yet been imposed on the entire thing. Yeah, we imposed this boundary condition on the part for z only. But we didn't impose this boundary condition on the entire linear combination, on this general solution. This general solution does not obey this boundary condition yet. And this is what we're going to do in the last step. So, if we put z is equal to L, what we want is to have this entire sum equal to v. In other words, we must have that sum we can cancel out the v's in the sum and this side, so we have 1 is equal to this sum over here. Now this looks like a Fourier expansion in 2 dimensions, and it is a Fourier expansion in 2 dimensions. So you're going to use exactly those techniques to find these constants a, L, m here. Now in Arfkin's book, what Arfkin, Weber and Harris observe is that a, L, m can be written as a constant a of L times a, m, and then they just find the general form of this. And you can have a look at how that's done there. Or you could just say, I'm going to find a, L, m as follows. And now I'm going to use the following result. So if I is equal to the sine of our integration range for both x and y is 0 to c. I hope you understand that, because the box has a length c along both directions. So we're going to use this result that the integral from 0 to c of sine L pi x over c times sine of L prime pi x over c with respect to x is 0 if L is not equal to L prime, and it's going to be c over 2 if L is equal to L prime. In other words, this integral is equal to c over 2 times delta, Kronecker delta of L prime. And this should be familiar from your Fourier series, so just go back over that if you've forgotten how that works. Now what we're going to do is take the inner product of a with x L prime and y m prime. So to remind you, this is what equation a is, and this thing here is x L of x, and this thing here is y m of y. So we are taking the inner product from the left with x L prime of x and y m prime of y, and this is effectively written as follows. So we have x L prime of x, the inner product of x L prime of y m prime with 1, because there's a 1 on the left hand side, and that's equal to the sum over the L and m, and you have the inner product of x L prime y m prime with x L y m. Now you can perform these manipulations using the Dirac's notation, or you could keep to the integral notation if that's what you prefer. Now if you're unsure as to what I'm doing and how is it working, then stick to the integral notation and just take your inner products using the integral form. But if you're comfortable with the Dirac notation, what you can see here is that this can be split into an inner product for the x coordinate only times an inner product for the y coordinate. So I've split this 1 into two ones, 1 times 1, and then you put 1 there and 1 there. And here these two terms depend on x, and these two terms on y. So I split this inner product into two inner products, one depending on x and one depending on y. Now, from the result we have above, this term here is a c over 2 delta L prime L, and this one is c over 2 delta M prime M. Nice and easy. And these two Kronecker deltas are going to collapse these two sums into one term only. The only term that will survive will be the term for which L is equal to L prime and M is equal to M prime. In other words, you will end up with A L prime M prime c over 2 times c over 2. On the left hand side, we need to evaluate what this is. Now, this is simply the integral from 0 to c of sine L prime pi x over c dx times 1 if you wanted to keep the 1 there. And that evaluates to minus c over L prime pi and brackets 1 minus 1 to the power of L prime. Now this is valid when L prime is greater than 0. Remember, we do not allow L prime or M prime to be equal to 0. So we don't need any further conditions on this. So that lets us then evaluate A, L prime, M prime quite easily, because on the left hand side we simply have this big complicated looking expression, but it's not complicated at all. And then we have A, L prime, M prime times c squared divided by 4, and then we drop the primes because it's just a dummy index. I mean, I don't care about the primes really. So A, L, M is 4 over pi squared Lm, and then we have these constants in the numerator. And now you realize that if L is an even number, then minus 1 to the L is plus 1, so this is 0. Likewise, if M is an even number, then this is 0. If L and M are both odd numbers, then each of these terms in the square brackets becomes 2. So we can then say that ALM is 0 if either L or M are even, and if both are odd, then ALM is 4 times 2 times 2 from each of these divided by pi squared LM, or 16 divided by pi squared LM. And that lets us write the entire solution down in all its glory. That psi of x, y, and z is the sum, double sum, over odd L and M only, where L and M both go from 1 to infinity over odd numbers only, of 16 over pi squared Lm sine L pi x divided by c sine M pi y divided by c v times the sine hyperbolic of gamma Lm z divided by the sine hyperbolic of gamma Lm L, where gamma Lm is L squared plus M squared, the whole thing times pi squared over c squared. Now you know everything in the solution, and this is the full solution to this problem. If you were an adept at plotting such functions, you could, sum up the first few terms and actually visualize what it looks like inside that box. I haven't done it, but if you like using your Python skills with matplotlib, this is your chance to shine and actually plot this in 3 dimensions, or possibly take sections in different z planes and find out what this looks like as a function of x and y, or y and z. So I hope you've seen that although there were many steps to the solution, none of the steps were too bad. They were quite well defined. We've got a fully determined solution. There are no unknown constants in that solution. Then the quantization of the x, y, and z parts arises from the boundary conditions. That has quantized the allowed values of those lambdas and mu's. Yep. And this is going to be the same thing. You're going to see the same kind of quantization arising when you solve the Schrodinger equation. The quantization condition always arises from the boundary conditions. Without the boundary conditions, you won't have quantization. The coefficients of the expansion were determined using ideas from Fourier series, and all of the functions capital X, capital Y, and capital Z were determined by solving ordinary differential equations. So what we've succeeded in doing is partial differential equations, I should set plus the separation of variables, is equivalent to ordinary differential equations plus Fourier series plus an inner product plus basis sets. Cool, right? Because you've now been able to tie all of these together into partial differential equations. And this technique of separation of variables is extremely powerful. You're going to use it for solving the Schrodinger equation. I've shown you how to use this technique for the Laplacian in x, y, and z coordinates. In subsequent lectures, we will look at how this can be done for spherical coordinates, for cylindrical coordinates, and later on you'll see that it can also be extended for systems which have more than one particle in them. But that becomes progressively harder. All right, so we'll stop here. I hope these examples have been useful and you've enjoyed finding a full solution to a partial differential equation for the first time. It's kind of cool when you're able to do it yourself. All right, thanks for watching, and more later.